So there are a couple things that need to be said about the interplay of acceleration and velocity. Part of where the confusion with these issues comes from is that we are using velocity in a really specific way in this class. It is rigorously defined, whereas in real life we use it interchangeably with speed, but it's not interchangeable with speed. They are related, but not the same thing. So let's just take a test case here. Let's say that I have an object which has a velocity which looks like this. We'll assume that this I've defined somewhere positively, the positive sense is to the right. So I have an object with a positive velocity, and I'm going to apply to this object a positive acceleration. Sorry, lowercase a. Strictly speaking, I should point out these are all vectors, and so what I should be doing is putting the vector sign over the symbols. I frequently will not do that just because it's kind of obnoxious to have to do it. Whether or not I'm speaking about the vector or its magnitude, which is just a scalar, should be clear from the context, but these are definitely vectors. I've got a velocity to the right and an acceleration to the right. What is going to happen? I don't think it's too hard to see that in this case, if this is how I've applied it, that the speed increases. The velocity vector gets bigger, right? The velocity vector is still going to be pointed to the right. It's going to increase in magnitude, which means this vector gets bigger. And if I'm talking about the speed is going to increase. This is what you do when you're driving down the highway and you need to pass somebody and you hit your gas and you speed up. You're applying an acceleration in the same direction as your velocity. All right, well, let's flip it around. Let's say that now, in this case, we have a velocity vector to the left that is negatively oriented, and we have an acceleration to the left, negatively oriented. Okay, well, by analogy with this, the acceleration is still in the same direction as the velocity vector. So what has to happen is that the velocity vector gets bigger. Now, the confusion comes in because the velocity gets more negative, right? It's getting bigger, but it's still pointed in the negative direction because the acceleration is also negative. People seem to have trouble with it, and I certainly did when I saw it the first time. The velocity gets more negative. Well, that has to mean it's slowing down, right? No, if the velocity vector gets bigger, that means the speed increases. Remember, the negative sign is only there to tell you direction. This is moving in the negative direction. So if the acceleration and the velocity vector are in the same direction, no matter what you've called negative or positive, your object is going to speed up. Just imagine, you flip your coordinate system around here and define to the left as positive. What's changed physically? Nothing. So nothing can change physically as to what the object is doing. And in that case, I think we'd all agree. If to the left is positive, we'd all agree that this is speeding up. Has to be speeding up if I call to the left negative. I haven't changed anything physical. All I've done is imposed a different coordinate system on it. So if the velocity vector and the acceleration vector are in the same direction, the object will speed up. Whether or not that's getting more and more positive or more and more negative depends on your coordinate system. All right. More interesting case, maybe, is what happens when they're in different directions. So let me take a velocity vector to the right and an acceleration vector to the left. Well, what's going to happen? Well, this is like when you're pulling up to a stop sign and you hit your brakes. We're going to find out later in the semester that what that's actually doing is causing a force to be applied to your vehicle, which is going to produce an acceleration. For now, we'll just stick to just talking about the acceleration and not worrying about where it comes from. But the acceleration is in the opposite direction of the velocity, which means the velocity vector gets smaller. What that means, regardless of the direction that you've defined to be positive, the object is going to slow down. When the velocity vector and the acceleration vector are exactly opposite, the object is going to slow down. Now, if we think through this motion, so maybe at the first instant of time, this would be t is equal to 0. This is right when I start my stopwatch. My velocity vector looks like this, and I apply this acceleration. Then later, what I'm saying is my velocity vector has gotten smaller. And then if I keep watching, even later, my velocity vector is getting really, really small, which means the object is getting really, really, really slow. Now, that can't go on forever, because at some point my velocity gets to 0. So at some point, I have no velocity. Later still, my velocity is equal to 0. Okay, well, what if I'm still applying the acceleration, right? In all of these cases, I've got an acceleration that looks like this. Let's assume that I'm applying this acceleration, make sure you can see that, constantly. Well, it means when the velocity is 0, I'm still applying the acceleration. So what's this thing going to do? Well, it's 0 for just a second, but then it immediately starts going in the opposite direction, right? And because the acceleration is now being applied in the same direction, the object is going to speed up in the negative direction. So this is the idea of coming to a stop. Right? You're going at some speed. That speed gets smaller and smaller and smaller. You come to a stop. But if the acceleration is still being applied, your motion, in a sense, turns around. Now, if you look at this and go, well, I don't know, what's going on there? I invite you to take some object around you, a ball, a pencil, or something, throw it up into the air, and then catch it on its way down. And watch what it does. What does it do? It does something like this. Like this, right? When it leaves your hand, it's going up, up, up really fast. But as it gets higher and higher, it slows down to the point where it stops. And then it turns around and starts speeding up to the point where you catch it again. Why does it slow down? Because there's an acceleration directed oppositely to its velocity. We know where that acceleration comes from. It comes from the force of gravity, right? The Earth is pulling down on your ball or your pencil or your cat, whatever you threw up. And that force doesn't stop at the top. So the acceleration of this object is down constantly. Gravity always points down. So any acceleration caused by gravity is going to point down. So if the initial motion is up, it gets smaller and smaller. The velocity gets smaller and smaller and smaller to where then it stops. But it doesn't just hang out there in the air. It turns around and starts falling down because the acceleration in all points is pointed down. Now, careful. The velocity at this point is 0. This pin, if it were to go up in the air, would stop and come back down. How long is it 0? For a second, a minute, an hour? A fraction of any of that. It's instantaneously 0. It only hangs out there while it stops and then it turns back around. It does that because the acceleration is acting on it. So take this to the bank. Just because the velocity happens to be 0 at some point does not mean that an object is not accelerated. In point of fact, it could be accelerated. Now, if the velocity is 0 for a long period of time, that then will mean that the object is not accelerated, but an instantaneous 0, you still have an acceleration.